So let's look at another example of a spectral deduction. And if we look at the initial data here, we've got, of course, the infrared spectroscopy, which tells us about functional groups, the mass spectroscopy, which initially will tell us about a molar mass normally and allow us to work out a chemical formula, and then the nuclear magnetic resonance, which tells us about those unique and special environments for each of the hydrogens on the carbon chain. So let's start with the infrared. And we have the peak at 2962 wave numbers. And of course that's right in the range for a carbon to hydrogen stretch, as we'd normally see it. Nothing unusual or exciting there. And the only other thing to report are these vibrations at 1477 and 1367, which are the bending vibrations in plane at 1477, sometimes called scissoring, and then out of plane bending at 1367, which we sometimes call rocking. So no real signs of any major functional groups there, just a normal run-of-the-mill hydrocarbon. If we look at the mass spectroscopy, there is something a little bit more interesting than just a molecular ion peak, although it does concern the molecular ion peak. We can see those two peaks close together, separated by 2 units of mass, and from the size of the peak it looks like a 3:1 ratio. Is it just a fluke? Well, if we look just a little bit further down the mass spectroscopy, we see that 3:1 ratio again. So it doesn't seem like a fluke. It looks like there's something there on the molecule which lasts for a while before being knocked off. And of course we know about a halogen and that 3:1 ratio. It's the chlorine isotopes, chlorine-35, which makes up for 75% of the chlorine in the universe, and the chlorine-37, which makes up 25% of the chlorine in the universe. So the 75 to 25, the 3:1 ratio. When we see that kind of ratio repeated down these mass spectra, it's telling us that there's a halogen, like chlorine in this case. So from that very last peak at 108, we'll use that for our molecular ion peak. And of course we take into account the mass of the chlorine, using the heavier of the two, the 108 rather than the 106. That means it must be the 37 isotope, leaving us with 71 units of mass. And that's what we'll divide by 14 into the number of CH2 units, which seems to go in just over 5 times with 1 extra unit. So that 1 extra unit is most easily explained with an extra hydrogen. So it looks like the formula is C5H11Cl. And of course the chlorine is taking the place of a hydrogen that we'd normally find. So imagining that chlorine as another hydrogen, that would be C5H12, which would suggest complete saturation. So there's no double bonds and no ring formations, which would cut the hydrogen count down by 2 each time, just a chloroalkane. So let's look at the NMR and the peaks we have for the NMR. Just 2 peaks, 3.19 for 2 hydrogens and 0.89 for 9 hydrogens. That tallies with the chemical formula, which suggested 11. So we don't have to double or treble this ratio. So the peak at 3.19 ppm, if we look at that, that's of course a singlet, which means that those 2 hydrogens don't have any non-equivalent neighbors on the next carbon. And we know because it's downfield at about 3.19, those must be hydrogens which are on the carbon, which is directly connected to the halogen itself. Halogens, of course, we expect between 3 and 4 ppm. It's the only reason we can explain how far downfield that peak is. And there's no non-equivalent hydrogens next door, hence the singlet. Then the peak at 0.89, which is for 9 hydrogens. Of course, we can't get 9 hydrogens on one single carbon. So it's three sets of three equivalent hydrogens. And likewise, because it's a singlet, on the carbon next door, there aren't any non-equivalent hydrogens next door. So that explains the vast majority of the molecule just there. Remember, when we look at the chemical formula, it's C5H11Cl. So one carbon explained, then another three, which makes four. So that that neighboring carbon, which doesn't have any hydrogen, it must be the same carbon to make the fifth and last carbon in the molecule. So we can easily patch these jigsaw pieces together and say that we've got this 1-chloro 2,2-dimethyl propane. 1, 2, 3 carbons in the main chain. And we can check that out again. The three methyl groups, all equivalent, with no hydrogens on the neighboring carbon, giving it a singlet, and it's downfield from the chlorine atom. And then on carbon number 1, we have the two hydrogens, which again have no non-equivalent neighbors, so it's a singlet here, but it's downfield because of its proximity to the chlorine.